Okay, now that we have the fundamentals down and we have a definition of a waveform for FM synthesis, I want to dig in a little bit more and examine the effect of some of these parameters that I can vary here. So here's just my definition to repeat it, and here's a little bit of code, that we wrote last time to make the waveform. Again, look at how simple it is. No loops or anything like that. Just two sinusoids, one fed into the other. I'm going to use a tool which is going to be a bit of a sneak preview to something that we're going over in the next unit. So I'm going to show you something called a spectrogram, because I want to know sort of what harmonics are in the sound here. So I want to do the inverse of what I've been doing. Up to this point, I've been saying, well, let me decide which harmonics I want, and I'll add them in. Now I want to say, well, I'm doing this weird thing. It sounded like I was making sounds that were a bit like what we did in the exercise at the very beginning. Can I verify that? Can I see that there are harmonics? So I have to actually figure out what frequencies there are over time. So now I'm going to show you something called a spectrogram. So I'm going to take, carrier frequency 440, modulation frequency also 440 for the moment. And this, I'm going to have this modulation index. So it's called, I forgot to write that. It's called the modulation index to be 1. And so here's the sound. And what I see is, okay, look, this is supposed to be a 440. Let me zoom in a little bit. Okay, so I see, all right, so what this plot is showing is over time what frequencies are involved. And so the x-axis is time, the y-axis is frequency. So I can see that, there's a 440 there. There's also an 880. There's also a 1320. And there's a 1760. So I'm getting the harmonics, right, an integer multiple here. So that's kind of cool. So let me zoom back out. Okay, so it looks like, I'm getting the first 1, 2, 3 harmonics, maybe a bit of the fourth. Now here's what's very interesting. If I increase this modulation index, I get a bunch more harmonics. So here it was with 1. Here it is with 2. Let's go up to 3. So we didn't get any more, but they were all a little bit stronger. So the math here is a little weird. Okay, I'm not going to get into the math. It's sometimes a little hard to predict exactly how many harmonics you're going to get. But the rule of thumb is the higher the modulation index, the more harmonics you get. Okay. Let's dial this all the way up to 10. All right. So already this is amazing. Why? Because at the very beginning of the module, I showed you when you wanted to add this many harmonics, you had to do it on a loop. And every loop, you had to generate a completely different sinusoid from scratch. Well, guess what? We still only have 2 sinusoids here for all these different frequencies. So this is really different from any trick we've pulled so far, right? I mean, in the Risset assignment, we were able to aggregate frequencies that were the same, maybe with a different phase shift. But here we're able to aggregate a whole bunch of harmonics into one waveform expression that has 2 sinusoids. That gives us an amazing amount of control. Okay, so that's really cool. So that's, you can do a lot just with the modulation index. Okay, so again, very different sounds there based on how many harmonics I have involved. Let me dial this back down to like 2 for a moment. Okay, now what if I mess around with the modulation frequency? That's the other parameter. And I'm going to make this to be really in terms of the carrier frequency for a moment. So let me make it 2 times the carrier frequency instead of 1. Before it was 1 times 440. Now I'm going to make it 880. And let's just look at what happens here. So it might actually be helpful if I kind of want to show these images both at once. So let me do it. Just copy this down here. Okay. So what do you notice? Basically, the ratios double. All right. So before we were jumping in actually the harmonics, every harmonic. So we were going 440, 880, 1320, so on. Here we're going 440, and then we're jumping directly to 1320. So actually the interval between successive frequencies is now double the base frequency. Well, guess what? That matches exactly what this is. So it turns out the modulation frequency can be thought of as controlling the interval between successive frequencies that you add. So that's the picture. What about what we hear? So here's the original. Now here's with the modulation frequency, twice the carrier. So this sound gets a little, people will say, brighter. What it means is that there's the same number of frequencies, but the frequencies involved are higher. We perceive the same pitch, but this one is dampened. A little bit of a damper sound compared to this one. And just to show you, I can do every third, right? Now this starts to get a little interesting. So I see, I don't just see every third. I mean, I do. So let me zoom in a little bit. So we're discovering this just like Channing, right? Okay, so what I see is I do see the 440, and I do see 440 times 3 after that, but also see these other ones that are close, that are within 440. What's happening is you actually are going to a negative frequency and reflecting back. So this is really negative 880 reflected back. Okay, so it's sort of, what it turns out is actually you add harmonics in both directions. That's a little weird. So you actually you add an interval of 440 when I have this ratio of 1 between the modulation frequency and the carrier frequency. I add 440, 440, 440, 440. I never noticed, but I was actually adding 440 the other way, and they were getting reflected back. There's a notion of a negative frequency that's involved here. Now that I actually have a ratio that's not an even number, I'm going to see something a little weird, which is, I started 440. I jumped up by an interval of 3 times 440, but I also jumped the other way by an interval of 3 times 440 and then reflected it back. So this is very interesting. What it does is it gives you the first harmonic, skip 1, third harmonic, fourth harmonic, skip 1. And let's keep going. So it gives this pattern, which is a little different. So we kind of left out every third harmonic. That's a sound. Okay? It's a different sound. And we were able to get it simply by changing a single parameter, right? We didn't have to do anything fancy in our loops. Okay, so now you're starting to see the degrees of freedom here, the things that we can modify. Now let me show you something truly wacky. Okay. So what if I make this maybe not an integer? What if I make this the square root of 2 times the carrier frequency? Let's listen. So here we get something that we say is inharmonic. These do not make nice ratios. We may consider them to be, dissonant in some ways. However, there are actual musical instruments that sound this way. And those are things like bells. So this really is the bell sound. I don't know, we could try another irrational number. Maybe pi. Okay, so we get some weird sounds. But just look at this variety here. This is very interesting. Okay, now there's one last thing I want to show you. I promised you that we would make that bass note from the Kenny Loggins song. So I just want to show you how you can do something that sounds like a plucked string in this framework. And we've already looked at plucked strings. But again, let me review it, and I'll actually look at this image to show you what's going on. But you know, we came up with this simple model where we said, you know, what we're going to do is we're going to choose a bass frequency. So whatever my note, you know, like my violin a moment ago was tuned to this. And what I'm going to do is I'm going to create this decay. So I can control how much the decay happens. Okay, now what I'm going to do is to say for I in range some number of harmonics. So I'm going to start off doing the loops just to show you. And what I'm going to say is y plus equals np dot cosine 2 pi f0 I t times this decay raised to the I power. So we talked about this before, but I just want to do it again, and I'm going to show you the spectrogram. Okay, so it sounds kind of like a plucked string. Okay, but let's look at this thing. Okay, so what we see is we start off with a bunch of harmonics, but let me zoom in a bit here. But the higher frequencies die out quicker. That's why I'm raising this decay to a power. So I have an exponential decay, and I'm raising this to a power. So the lower frequencies last longer. Well, here's the totally incredible thing. So we showed that, you know, if you choose things in integer ratios, you're going to get integer harmonics, integer frequencies ratios. If you start that way, but you also, okay, and we also saw that the modulation index impacted how many frequencies there were. Let's see if I can do something similar to what I did in the loop here. But this time I'm going to do it with FM synthesis. So instead of having the modulation index be a constant, I'm going to start the modulation index out higher, because it seemed like when the modulation index was higher, I got more harmonics, right? But maybe I'll make the modulation index decay exponentially so that some of the harmonics die out. Let's try it. So I guess I'll say I maybe is equal to 10 times np.exp negative t. I'll do the same as the other one, so I think I said negative 2t. Okay. So now I is actually an array. The modulation index is going to change over time. Let's listen. I already see it. It looks like I'm on the right track, right? I get the same kind of pattern that I did here. Okay. So maybe a bit like a string. Let me make it shorter. Maybe like decay even. Maybe a little more. Kind of sounds like a string. Look, this is amazing. We never... Look, I had to loop through a bunch of stuff here to do this. Here, again, all I have to do, I just have to add one more, you know, I had this parameter. Before it was a constant, now it's actually time varying. Just to show you the plot, let me plot this. So this is the modulation index. Over time, so you can see that it goes down. Get this thing, it sounds a little bit like a string, and it certainly, I would say it certainly sounds like I certainly recognize the 80s synth version of a string there. What if I, you know, maybe I'll make this a little smaller to start with, so fewer harmonics. Now it sounds a little more like this one, maybe. Definitely has a different timbre. Okay, so FM synthesis is going to have a pretty unique timbre, but we get the same qualitative behavior, which is very interesting. Okay, So quick exercise, we're going to try to make that Kenny Loggins note. It's going to be an E, a low E. Let's see. I guess an E that's 2 E's below concert A. So we'll try that. All right.